Hello, everyone, and thank you for joining us for today's webinar on DARPA's Ocean of Things program. I'm Megan Nicholson, Program Officer for the Government University Industry Research Roundtable and your moderator for today's webinar. The Government University Industry Research Roundtable, or GUIRR, is the oldest roundtable of the National Academies of Sciences, Engineering, and Medicine. Its focus for the last 30 years has been the health of the nation's science and technology enterprise. The Roundtable brings together the senior-most representatives from three sectors, government, universities, and industry, to define and explore critical cross-cutting issues related to science, technology, and innovation policy on both the national and global scales. Roundtable members meet in Washington 3 times a year, but we also use these monthly webinars, which have been part of regular GUIRR programming since 2012, to engage the public and science policy communities, as well as folks on the Roundtable between meetings, to consider issues that merit interdisciplinary and cross-sector examination. I just want to go over a few logistical notes to keep in mind before we get started. First, if you have any technical issues during the event, you can contact Zoom technical support at 1-888-799-9666 and select option 2. Also, the audio for today's event will be streamed through your computer speakers, and the webinar is being recorded. The recording will be archived on the GUIRR website, and you'll get an email from me when it's available. We will be taking questions through the Q&A box along the bottom of your screen. You can submit questions at any time during the webinar, and we'll get to them after the speaker has concluded their presentation. Since we are recording, I want to remind everyone that any question you submit may be read aloud and included in the recording. All right, so on to today's webinar. The DARPA Ocean of Things program seeks to enable persistent maritime situational awareness over large ocean areas by deploying thousands of small, low-cost floats that could form a distributed sensor network. Each smart float would contain a suite of commercially available sensors to collect environmental data and activity data about commercial vessels and aircraft. The floats would transmit data periodically via satellite to a cloud network for storage and real-time analysis. As you can imagine, both the float design and the analytics software for an ocean-based Internet of Things offer a number of engineering challenges. Here to discuss those challenges and the Ocean of Things program is John Waterston, Program Manager in DARPA's Strategic Technologies Office. John's been with DARPA since 2017. His interests are in maritime autonomy, undersea warfare, distributed sensing, and non-traditional communications. Prior to arriving at DARPA, John was the Senior Program Manager at SRI's International Advanced Technology and Systems Division. There he led defense research programs in various technical areas to include cyber warfare, Arctic sensing, and unmanned vehicles. Outside of industry, John serves as a commander in the U.S. Naval Reserves, where he applies his submarine operational experience to support naval warfare systems integration. I'm going to turn it over to John now to discuss the Ocean of Things program, and then we'll take questions from the audience. You can submit your questions at any time during and after the presentation through the Q&A box on the bottom of the Zoom screen, and I'll start reading those submitted questions after the presentation is complete. We'll have around 30 minutes for conversation, so please stay tuned and ask questions. John, thank you so much for being here today.
Hey, thank you, Megan. It's great to be here at National Academy of Sciences to discuss the Ocean of Things program. For a little background, DARPA, I've been at DARPA 3 years. I got 1 more year left, so we're there as a short-term program manager, but hopefully we're there to make a significant impact. And the Ocean of Things program is designed to benefit government, industry, and academia, so I'm glad we have such a diverse audience out there today. And we'll talk about this program that's been going on for just about 1 year. So the thesis of Ocean of Things is based on my understanding that the ocean is so large, yet even with the number of sensors that we have out there, we need some way to augment them and provide an understanding of what's going on between the existing platforms. And in this picture I showed notionally, satellites and fishing boats and ships and the existing drifters and buoys that are out in the ocean today. And the solution that we're presenting is to use thousands of intelligent floats to drift along the ocean surface and fill in those gaps. In order to make that economical, they have to be able to persist for a long time and take advantage of the commercial advances in low-cost computing and low-power computing that we've seen based in the cellular handheld device world. The other enabler of this type of technology is ubiquitous satellite communications. So these floats use iridium because that's what's available today at large global scales. But I imagine in the next few years, we'll have a new constellation of low Earth orbit satellites that can work at lower powers and lower costs and enable this to continue to scale as the program continues. Another assumption that we make is each one of these floats kind of carries one type of sensor so that we're not combining high-end sensors on floats so that these keep at a very low cost. And the goal of this program is at scale development for floats to be manufactured for $500. And that's very achievable based on the bill of materials we're seeing performers use today. So let me kind of talk about how this sensing activity occurs. And it's an edge sensing problem is the way it would be discussed in the academic literature, where these floats now not only have the sensors, but have processors to identify what is interesting and run signal processing algorithms and detection algorithms against those data streams so that they can notify with reports and provide these reports to the cloud for then follow-on analysis. So at the top of this chart in the grayish color is what's going on board the float. So periodic measurements of temperature, the accelerometers, the GPS position, those things are important, but they're kind of lower priority. And as the float periodically updates itself and tells whether its battery life is good and whether it has enough signal strength, those types of things will come out periodically. But there's also an event-driven or activity-driven report that's that second row, where if a whale goes by or a helicopter flies overhead, the float knows there's something abnormal occurring in its environment and one of its sensing modalities, therefore encapsulates that, puts it into the satellite queue and transmits that in near real time. So this allows for queuing and anomaly detection in near real time with the system. On the right-hand side, it kind of shows what I was talking about, where we have a 3-year-old cell phone. Think about that's what the hotel sensors there are in gray, the microphone, the GPS, accelerometer, and a temperature probe. Then on top of that, we add that mission sensor of a software-defined radio, a magnetometer, a hydrophone, or a camera. And that provides the whole idea of a complete float. So when both the scalar measurements and these activities-based reports come across the Iridium link, we're then able to place these into that cloud infrastructure where our analytic teams look at the reports and try to generate tracks and other types of data products for use. So things like there was a fishing vessel that went through here, right? And then maybe that's the most basic report. And then that final layer is as we build multimodal detections, we'll be able to tell what type of fishing boat it was. Maybe it was just a surface vessel, and now it's a fishing because we hear the fathometer and fish finding sonars, and we get its AIS confirmation. So now we're able to build this library of activity going on in an area and understand a lot about the ocean environment, build this kind of robust spatial temporal database for discovery and analysis. So these are pictures from our most recent kind of float deployments. We realized that this type of high resolution, sub-mesoscale ocean surface data streams didn't exist. So I had to build thousands of floats here in phase 1 of our program. So we had 3 hardware performers who built floats. So we had Xerox PARC, Arete, it's a small business in the Northern Virginia area, and Numerous, which is a small business in the Seattle area. Each build their version of what they thought an Ocean of Things drifter would be. Numerous made their float out of cardboard to minimize its environmental impact, Arete used aluminum and wood to provide that buoyancy and minimize its environmental impact. And Park had, I'd say, the most innovative material selection of glass, so that their float upon end of life would, shatter and disintegrate and be very inert to the environment. So you can kind of see the size of these. They're about less than 10 kilograms, 6 to 10 liters. They have very low height of eye. They are drifting right in that first kind of half a meter. They do not have drogues. They don't have long tethers on them. And we built, in this first phase, 4,500 floats, and we probably, just in our environmental and validation tests so far, deployed right around 250 floats, and we're getting ready for kind of March, April timeframe to do larger scale deployments, both in Southern California and the Gulf of Mexico. I think I have slides on that later. So I don't think I have to inform this community about what drives things in the ocean, but I mean, it's the currents of the ocean, the waves and the direction of those waves, and the winds. So those are the three motion vectors that each one of these floats will be driven by. And the current ocean models aren't at high enough resolution. So we've been investing in improved high-resolution ocean models at kind of the 1 kilometer scale that take into account the wave motion and the currents as well to then predict where these floats will be. Because the value of these sensors is when they persist in the environment for long periods of time, right? We're getting more bang for the buck and more understanding about a specific area. The graphic in the lower right was based on research done out of the Carthay Drifter program, which was funded by the Gulf of Mexico research after the the BP Deepwater Horizon spill. They put out, I think this graphic's a few hundred floats. I think this is 300 floats starting at Deepwater Horizon, and where you see the concepts of, well, the ocean manifolds will cause things to converge, but then a wind event will come along, and eventually over time everything will diverge. So you do see both simultaneously concepts of distribution and convergence. And the good thing is that it holds to the kind of the normal, to the 4/3 power dispersion types of rules that's in the literature, but you're able to see this type of structure. And the most recent deployments that we have are following similarly on these points. And once we have our first large-scale deployment, I think we'll get a similar type of graphic out there. I also see that these floats will complement existing sensing, whether it's remote sensing or other higher resolution, whether that's autonomous vehicles or buoys, the ocean buoys that are out there, that these things are complementary and allow their data to be applied to different locations. So here's an example of a data product that we did based on National Academy. This was a National Academy of Science deployment. Researchers from the University of Rhode Island took about 50 of our floats out to sea. This is back in September, I think, yeah. Yep. Late September, first week of October, and displaced floats in a few different areas. So what you're looking at is one of our internal GUIs where you can investigate sea surface temperature kind of in those hexagons. You can look at this, whether it's trajectories over time, you can look at average temperatures, you can look at this as a video and how those sea surface temperatures over time. And then the goal was then to take these sea surface temperatures and then assimilate them into high resolution models, look for different activity sources, whether that's, a ship driving through and things like that. So our analysis teams are still looking through this types of data, and we want to offer it to the community that, that this data is available and that we are making it available to researchers right now. So if you want to contact me afterwards or go to the Ocean of Things website at DARPA, we'll have links kind of, I think, by the mid-February timeframe, early as March. We're running through some challenges there of getting the releasability of the data. There's nothing there, but there's a public release process with the government. So we're working through that, and we'll have the data sets available in kind of net CDF files for future researchers. Here's an example of one of the mission sensors that we used. This was the hydrophone. The data here is taken with our government partner is Naval Information Warfare Center Pacific in Point Loma. So this, we have our environmental test data that sits there at the San Diego harbor. They have a few piers where these floats are deployed, and this is just looking historically over the acoustic sensor and how we're actually looking at power spectral density by octaves of processing, and by comparing the relative amplitudes, you're able to find activity where, in the middle of the day, it's obviously louder. You can see some things like that. You can see ships coming by these floats in the harbor. And we're also finding that the acoustic data is tied to the wind speed. So we're able to create these derived products of wind speed, activity, what's the noisescape? It's a question that I've been asked by a lot of environmental researchers is, how loud is the ocean when we're not there? So it goes into a lot of the calculations of, are we creating the impact to the ocean when we go do drilling operations, or when there's large shipping traffic, or when other types of activities are going on? So is that larger than just the wind or a storm alone? So we'll be able to answer some of those long-term, what I'll call climactic, or, so the climate or environmental concerns, at the same time where we're finding specific cases of activity. And so that's balancing, while the same data product is collected, two different user groups can use it in different ways. And that's one of the highlights of the architecture that we're building in this type of program. So here's another one of our mission sensors. This is a software-defined radio looking in the VHF frequency band. Notice in the Gulf of Mexico, there's a lot less noise in the RF band. So on the right-hand side is San Diego. On the left-hand side is the Gulf of Mexico, where you saw that the temperature plots 2 slides earlier. You can see things like the cellular data infrastructure at all various different power levels. We're trying to find, are these, VHF channel 16, things like that. Other types of communication systems, and then tying the time signatures in the right. This one we're looking at all times, and just this is a power versus frequency plot, but taking that same view and then doing an activity-based analysis would allow us to see these same vessel progressing through the field. And that's again, the duality of the data. We have both activity here and both a survey of the overall RF environment. The floats now, like I said, have low-cost processors. Well, the ARM processors that you can get for $20 today are smart enough and powerful enough to run neural nets. So our performers have trained neural nets on traditional maritime images, and the instead of training them on the floats, they just build the classifiers and the weighting functions there, and so they process the images, get them down to low resolution so that we can transmit them over that Iridium small burst data, which I don't think I've said yet, but it's 340 bytes. So I like to say the floats tweet when they find something interesting, and that's pretty close to the right data size that's there. So here's an example of these low bitrate pictures, but you're able to see things labeled as people and buildings and ships from the San Diego Harbor deployment there at Niwot Pacific. So this was really interesting. We hadn't seen this until just about a month ago when this capability went online with these floats. When we deployed the floats back in late September, early October, there was some lows moving through the Gulf of Mexico, right? That's hurricane season, and we had a low that was left over just a little west of center in the Gulf. And one of the initial designs of the floats was metastable on its side. And the odd thing there was, like, we would note that it was dropping out of communications or was becoming less reliable. And so we were looking here at, well, what is the IMU data telling us about the pose of the floats? And then we were able to correlate where these floats were occurring and tipping more often. Was the initial theory was like a ship was driving by and that wave was causing it. That wasn't the case. It was just areas of higher sea state and a way to understand the wave spectrum. So we're trying to refine this type of product for those people who look at wave spectra and want to understand how those, larger, wave events propagate over large ocean areas. So is this Ann, I don't know if we can click on it, or does it play as a video?
Try.
Okay, oh, I did. Okay, I'm going to try to play this on a video. As I've always said, there's a PhD available for people who can embed videos into PowerPoint, and I'll offer them, confer them from DARPA, if you can do that. So here you're going to see these over time. There was a float on the back deck of the ship. We had 2 different manufacturers. That's the colorization of that. And so on the eastern side of the loop current, you saw that deployment, and then and then you'll see them disappear at end of life. The floats, based on an initial consultation with environmental regulators, the desire was for these floats to scuttle rather than drift at the ocean surface where they can interact with people in the larger marine ecosystem there. So I think the longest living float here lasted for 24 days, and these were the initial engineering prototypes. So this was great to see this kind of scale deployment, but we learned a lot of things in the reliability path. The other thing that that you kind of gain in this type of deployment is how do researchers interact with it? So how the back deck, or how do you update the firmware on these types of floats? There's a lot of value gained. But as these floats deployed, they were collecting on all of their sensors. So we have the trajectories, we have the temperature data right now that's available for release to, obviously back to the National Academy for their work in doing this cruise and graciously deploying these floats, but to other people who are interested about going back and looking at the data. The other thing is we saw, interesting, the red floats there, they had low survivability. We currently have a set of floats in the Gulf of Mexico right now, and they're not having that same problem. So we've corrected the survivability, and we're getting more value out of those floats, and our goal is to kind of, in the overall, by the end of the program at 3 years, have a float that lasts exactly a year, right? That's the design goal. These are the initial deployments of these, and so the engineering challenge of making a low-cost yet robust float is something that we've been really working through so far in the program. I didn't think that would be the challenge, but I think we're investigating a new part of the physical design space where the more robust you make it, the more cost there's involved, and so there's a natural point where we're still finding out what the best design could be. So that's the kind of the trajectory map of the float deployment. The colors there are sea surface temperature, or they're just, I think they're sea surface temperature. So interesting, you can see an eddy to the left of the main loop that's up closer to the Mississippi outflow region. You can see some of the diurnal forcing there at the surface layer of the ocean, something that's not well captured in some of the models, especially at these resolutions. Another thing that I like to see is the cross. So where one float moves is where another float was, and so one float sensor cross-checks another float sensor. So there's an idea that even with these low-cost, what I say commercial quality sensors, you're able to do mathematical cross-checks, assuming things like temperature doesn't change drastically when a new float comes in. So there's ways to look at this field probabilistically and improve their measurement accuracy because of the large number of floats that are used in one deployment. So as this video plays and probably ruins all your bandwidth out there, it kind of shows what we're doing here. And we've jumped back to the Santa Barbara Bight, zoomed in on Catalina and San Clemente Islands there in the middle of the image, just south of Los Angeles and Long Beach, and on the far right is San Diego. This is a great piece of ocean to deploy into because it's got a great mix. So it's the largest port in the United States with Long Beach and Los Angeles. It's a huge naval port there and a lot of interesting fishing and commercial activity in that, both at an environmental, so concerned about illegal fishing, looking at both, and then the oil and gas industry out here. So this is a rich area, and this is why we picked this as our primary region for investigation. It's also well academically understood and runs a very high resolution model, which is that 3-kilometer high SoCal ROMS model that you see at the top. However, in Ocean of Things, we were able to get enough data from some of our early deployments, and we were starting to build a 1-kilometer model. So this is a 1-kilometer, we ran a 3D VAR and a 4D VAR model there with the Naval Research Laboratory, and you're able to see a bunch of new features that don't exist in the 3-kilometer model, and this is really encouraging to us and shows how rich the ocean environment is as you dig in the scale. And so you're able to see these upwellings and the vorticity. You're able to see some of the tidal effects, and you're able to see where maybe the exact location of these temperature eddies and things like that are a little different in the high resolution model. And as we continue to constrain this high resolution model, we're going to, I think, have the best understanding of the ocean environment that's out there. And this type of results have been going on in the Gulf of Mexico as well, where we've built a 1-kilometer model there and working to assimilate our flow trajectories and temperature measurements into that type of data set. Going from the environmental, like back to the data and the activity. So these are 6 panels where each panel kind of represents the influence of a given sensor. So there's 2 ships with the red dots. They come together and they diverge, but they light up the field of floats. So this is modeled 4,500 floats in Southern California. But you can see that what we were kind of modeling, well, what would it look like if a float reported when it detected something on the acoustic channel or on its radar channel or on its camera channel? Each one of those sensors has a unique radius of regard and has a unique kind of detection criteria. And so are we getting enough reports to send off so that the cloud analytics can generate a track? And can we resolve 2 ships meeting and then diverging, right? And that, I think I designed this thought experiment as the most challenging example of tracking. It's not just saying on one course and speed and heading into San Diego, or it's not the ferry going to, San Clemente Island or something like that, right? This is, well, maybe there's 2 fishermen, they meet, they talk, and then they go away, right? So it's something that we thought would be a really challenging detection environment. And so we're not there yet. We don't have 4,500 float data, but this was a more looking initially through model data to see if we could create trackers from this type of data set. So this is a view of where we are at in the program right now. We're just entering kind of that at the end of the first quarter fiscal year 20, and we put out a solicitation for phase 2 hardware. So that is open and on the street. So if anyone can make lots of floats and does that low cost, I'm interested in your proposals. So you can find that, I think, a link both at the DARPA website and both on the OPM website. I think Sam talks about solicitations across the government. So notice, though, in phase 2, we're scaling from 3 performers each making 1,500 floats to 3 performers each making 5,000 floats. So we're scaling up and reducing the cost of doing that. But it is not a closed solicitation. It's a new solicitation that's open to anyone who can meet the requirements of the program. But it shows that we have us looking for a partnership to do that 3rd phase where we want to manufacture and deploy 50,000 floats. And so we're talking to NOAA. We're talking to academic organizations, and we'd love to find some more industry partners who would be interesting to either support or sponsor a certain number of those float hardware, while DARPA might cover or do a cost share to deal with some of the data analytics and processing of that so that you could get the analytical products from your data. The second technical area is our analytics team, and so that's both the government systems integrator, where we're using Amazon Web Services to do containerized analytic products and tools to give us real-time view of the floats. We have 3 performers that are working on float predictions, ways to command and control these floats, and then extracting interesting features from those data sets. So that's what they're working through right now. So in the view that you saw back a few slides ago, where we had that temperature map, was one snapshot of that type of data, and our performers are giving us tools to understand how the floats are behaving. I show SoCal as where our tests are going on, but phase 1 here, we're looking to do a 3-month deployment, and that's in the February, April. So we're working through the environmental regulatory concerns right now. So we're about to come into public release of our environmental assessment in Southern California, and we're doing the same for the large-scale deployment in the Gulf of Mexico. So we're working in parallel with these 2 regions so that we have a chance to get as many of these floats in the water and to increase as much understanding as possible. So that's kind of the end of my prepared remarks. I'd be glad to talk about any portions of this or any questions that are out there. Megan,
yeah.
to you.
No, thank you so much, John, for the presentation. I think it's already given our audience a lot of foundation to ask questions. They've already submitted quite a few. So I want to start with, we have a number of questions coming in from listeners about the kind of coordination between DARPA and other agencies in the federal government, including NSF, and how the Ocean of Things program interacts with Argo. What's the difference? Is there overlap? So can you talk about the difference between the DARPA program and the other federal agency efforts?
So DARPA acknowledges there's a lot of other ongoing ocean research programs. I think we're trying to make an investment here to create a new paradigm for ocean sensing and a way to modernize the analytics infrastructure of that. We have no restrictions on working with other governmental partners, whether that's the NSF, NOAA, Office of Naval Research. We expect and we'll give them full access to the data and really want to know, what do your customers need? Right? This has always been the question. I knew I could collect this information, and I have a lot of great software developers to create products. So I need that demand signal, and I want to provide this so that it shows the value of what we're creating here, right? I'm not doing this just for one type of data feed, and I didn't create this program saying, oh, I have to go detect a destroyer. If I don't detect a destroyer, I'm all right. I didn't design this program that way. It's like, I want to collect all the ocean's environment, and I think I'll find a destroyer in that, was really the base thesis. The Argo program is great. It has a much larger global scale effort. It's 4,000, 4,200. It changes every day. I go to their website. I love looking at what the floats do. My floats, really are drifters, and they're coupled there to the first, 50 centimeters of the ocean surface. So there's a different thing that we're doing. I think it's complementary to what Argo is doing, and I think we are focused on regional deployments. The largest scale deployment we would imagine in this program is that phase 3, and that's 1 million square kilometers. So for frame of reference, the Gulf of Mexico is like 2.8 million square kilometers, depending on how you calculate that. So looking at that, where one float is per 20 square kilometers, and what type of spatial temporal resolution that resolution gives you, I think will be a game changer. Just what we're seeing today with 100 float deployments in the early test phases, where we can't even imagine what it's going to be with 1,000 floats out there. It's gonna give us a whole new awareness of what's available.
Community of interest. You want to talk about
Yeah, so there is a larger community of interest, and we're meeting kind of semi-annually to discuss and to put in those requests for the data. You're not restricted to only do that at those meetings, but engage. I think it's Ocean of Things at DARPA.mil. We have an email address. You can check it at, or oceanofthings.darpa.mil is the website. And go engage us. We'll get you the data. If you're a government person, we can give you access likely through your common access card to the data set and more of a real-time user view of what we're doing.
But it's open to non-government.
It's open to non-government government. It's just we are protecting the data in case we do too good a job of detecting things. I don't know it out there, but it's to alleviate any concerns with the scope and the sensitivity of our sensors. But in my mind, this is just a new way of sensing, and we're going to learn that it helps in so many other ways that there shouldn't be any security concerns with the data.
And sort of along those same lines, another listener is asking if how your project compares with other commercial ventures that are also deploying sea surface sensors at scale. Can you talk about commercial ventures?
I'm glad there's other commercial ventures that are out there. So I've been excited by, I don't know if I should mention, but there's a few. I've seen them at some of the IEEE Oceans events. A lot of them have proposed to our program. We realized that as a government, this was going to happen commercially. We wanted to move it forward. We see it happening globally, so we want to be at the center of this, understanding how to build the right analytics and get the right value from these data sets. So that's why we're doing that. There's already some pretty large-scale commercial deployments that are out there in the Pacific, and I've seen performers in Spain and in China doing very similar, what I'll call spherical floats, that are either loosely tethered, and originally I think a lot of people were looking at these to figure out when it was good to surf. So some of the initial commercial ones in the United States were off of Half Moon Bay and Mavericks, and could tell when the wave period was right that it was going to be a great time to go surfing. And I wish I worked at a business like that, so maybe I have some place to go after I get out of government service. But I think the other people are looking in the fishing industries, kind of local, more estuarial thing. And so as we're starting to move from the estuaries into the wide and the open ocean, we're right at the forefront of growing this.
Yeah, actually, that's a good segue to the next question. We've received a number of questions, actually, about sort of use cases for the data and where these sensors could be deployed, and especially concerning IUU fishing. Folks have been asking a lot of that, and also tracking ocean plastics. So I'm wondering if you can talk about that and whether you've looked into that field at all?
Yeah, so both of those I think are great users of what I call high resolution ocean current data. So from the fisheries world, we've talked about it really through government fisheries, through NOAA and bits like that, looking at could we identify illegal fishing in some of our marine protected areas and things like that. The bit of work that, so there's a regulatory protection enforcement side that we would like to work with NOAA there, but also in the commercial fishing world, I think there's bits of like, well, if we could find these temperature features or eddies that are very efficient to fish on, that we could fish with lower impact up to our quotas, and fisheries would be involved with that. The other question there was on ocean surface trash, right? And so by better understanding these currents and finding where the what I'll call the low energy vortices are and where the boundaries of those are, I think you'll be able, in our floats, they collect on these manifolds between the high currents and the low currents. And so they kind of give us a better insight as to where that trash would be. It would give the real-time monitoring. We have not partnered with the Ocean Cleanup Project. We'd be very interested to do that because that ocean surface is the thing that's missing in our understanding of the models today. the currents are tracked about 10-meter depth. The winds are at 10 meters above the ocean surface. So we need something actually at the ocean surface to know where that plastic is today.
I'm trying to get any ocean initiative.
Yeah, so we're looking at other ocean research sponsors around the country to answer things like that. So great question. As people get excited about this data, those are the way we want to serve those users. There's another thing I kind of maybe missed in my description is traditionally the government would buy floats, whether we're going to do this for meteorological investigation or we're going to do it to detect marine mammals over here, and oil and gas is going to do it over here for some type of regulatory concern. And we would build these stovepipes of data. Ocean of Things is trying to get everyone to create a fleet of these floats where we then share the data back across all users of that, so that we can kind of build a community in this, and then we can each ask of the data our own specific questions, because each float is detecting the same information no matter who buys it. It's the interesting side is all the different questions that can be answered on the analytical domain in moving forward.
So, and we have a number of listeners asking sort of about the properties of the float. So I'm going to kind of run through a list, and then maybe we can tackle them one by one. So someone is asking about the decommissioning process and how the floats will be removed after a year. Someone's asking about the power systems for the floats. Someone else asked if we're doing any research around whether the floats could be at risk for being eaten by fishes. And someone else is inquiring about biofouling. So maybe I'll remind you as we go, but if you want to run through those.
So I think all of those get back to this idea, how do you design a float that's both small and efficient and respectful of the environment and its impact on the environment? There is no decommissioning project, so these are not recovered floats. So these are expendable. So to gain the most value out of their float, they have to persist for a long time. So at end of life, or when commanded from the government, in this case, these floats will all scuttle. So think of them, which they will fill with water and descend to the ocean bottom. We have a geofence that we set up. So right now, we stay outside of the coastal waters of the United States. We stay outside of marine protected areas, and we can stay out of anything that we predefine before the float. So the floats are completely autonomous. They know where they are, and they prevent themselves from entering in any of these restricted regions. The floats also monitor their own health and say, hey, my batteries aren't healthy. And this will get to that second question about energy. So if we reach a low energy state prior to that, they have to have sufficient energy to scuttle, and therefore do not remain at the surface layer where that debris will remain. All the floats, well, one float designed here in phase one used alkaline batteries, just your standard alkaline batteries, and with the low-cost processors that are out there today, there was sufficient energy to run this multi-month mission. The actual challenge was more around waterproofing. So the energy wasn't the challenge, it was waterproofing and making that robust. The other ones that have a less, what I would call primary battery, they have a rechargeable battery pack and solar panels. So they're during the day, they don't use, or they recharge their batteries, and then overnight, they run off their internal rechargeable batteries. And so the size of their solar panels, right now are kind of about 12 inches by 3 inches, and there's 4 of those, so that's, about 1 square foot of solar panels gives you the right amount of power for a 24-hour lifetime of these floats. And so that's where there's a balance of, and I think solar panels right now are showing to be the better solution, and I think solutions going forward will have that solar base. We've looked for solutions to extract power from wave energy, and no one has given me a solution that scales down to this kind of 6 kilogram, 8 liter volume size that gets enough density from that. So there's a research out there. Traditional wave energy buoys have been much larger scale and much focused on things like that. So I'm interested in any approaches there that can harvest that wave energy, but have not been able to do that at the cost point and technology readiness level that we get at. So the longer these live in the ocean environment, you bring out this fact of biofouling. And so with the current floats, they have very little separation from the surface, right? So we do expect growth. We know that that's out there. You know, we don't have any coatings on there yet, but I think performers will have to think smartly about doing that, you know, whether it's ablative types of coatings that are out there kind of for traditional buoys, or, you know, they don't go deep like the Argo floats. The Argo floats go down to 1,000 meters and they squeeze all the things growing on the outside and they let go or die, and then they come back up to the surface and communicate. We're stuck there where there's the most light and stuff like that. As for interactions with marine creatures, there's not much known, right? These are large enough that I don't think that they'll be consumed. So they're not, you know, fish size. These are kind of larger size things. So we have, there's an unknown there, as, you know, if you could tell me exactly what debris animals will eat. It's all the research I've done, and you know, it's all the post-mortem type of analyses of marine mammals. The plastics and stuff are much smaller. So this isn't, I don't think this program is going to get much smaller. We're not going to have Coke can size floats eventually. I think you're going to stay here at the basketball size, 2-liter bottle or bigger size, so that they're not interacting with marine mammals or other things. So it's trying to minimize what they're look like. So, and then it's really about the size of deployment. So how do we get something out there that we can deploy, carry them, right? To minimize, you can't have these on 1,000 ships and do that. So thinking about their deployment and the cost to deploy these are not airdropped. I didn't say that earlier. So these all come off the back of a research vessel or a commercial vessel. And so how do we most efficiently deploy these is something, you know, you think about when going to these large numbers.
When I read out all the properties sort of questions, I missed one, which I think you spoke about during the presentation, but this person is asking if the floats are self-righting in high seas areas. Can you talk about that again?
Yes, they all are stable. I was kind of getting into one of the weirder things where they're metastable on their sides, and we've corrected that by adding a little more internal weight lower in things. So they are self-righting and we think stable in high seas. But again, how big is high seas? You know, do we expect these to go through the eye wall of a hurricane? Probably, at our current engineering stage, we're not there yet, and we would probably lose a lot of floats to damage. And that's where this is that margin that we're playing on between robustness and reliability, and purposely trying to invest in that, because I think there's more to be learned in that piece. So that is, I think, I didn't appreciate at the beginning of this program the challenge of making something low cost and survivable. And so that's been the most eye-opening thing. And that's a critical foundation to be a good steward of the environment, is so that you can so you live for the longest amount of time, therefore you maximize the value of the data, the value of the understanding that you provide in exchange for being able to operate in this environment.
Yeah, we actually have another sort of design question as well, if we can stick on this theme for a little bit longer. One of the listeners asks, how do you plan to deconflict the movement of water along with the sensor, like the sensor continually measuring the same water mass?
So I think that's interesting. This is where the edge processing, so I've talked about the physical design research. I think now you're getting into what I'll call the edge processing research. And it gets to the most expensive activity the float can do is not sensing, but it is to communicate. So the highest power activity is to turn on that modem and transmit your tweet. So how do you say it's recording temperature all the time, but maybe it only reports that temperature once per 24 hour, it reports that track, it says it hasn't changed, but maybe if it crosses a frontal boundary in the ocean and says, temperature changed by 1 degree C in the last 15 minutes. There's something interesting going on here. Let's make that report. So this is where we're trying to think about compressive sensing, thinking about differential sensing to get the right amount of data off that's interesting. The question might also have dealt with the fact that two floats move into the same region. So in the cloud, knowing it. So this is where the command and control layer, so one float doesn't know where its neighbors are, but the cloud knows where the neighbors are. And if two floats come into the same body of water, you might want to turn one float's duty cycle to near off, while the other cycle, so you can manage kind of the total energy, because it's about how many sensors do you need to extract the most information. So this is an information theory question of, well, now we're transmitting duplicate data, and you don't want to do that when you're at when that communications is the highest cost event. So you could make these last longer if you just had a fixed amount of energy, or you could allow them to maybe sample in different ways. So this is where now you can have a real-time feedback loop with the cloud saying, yep, there's two cameras that are only 200 meters apart. I'm not going to get unique data from those, so stop sending me images, because images are big files. I might care about your temperature data because there could be an interesting, high-resolution current feature there, but the picture feature isn't going to be interesting, or the RF features aren't going to be interesting because they're going to be identical. We're not there yet, but that's a phase 2 analytic product to give that type of feedback and extract the right information.
Great. Another question from a listener wants to know about ensuring the security of the data and the systems, especially if the components are made offshore. Are you worried about malware? Can you talk about the security of things?
So not concerned about that, because the thesis is very much like the calculus base. Like, the data from any one float is not valuable. The data is only valuable in aggregation across the field. We are protecting that. So wherever there is no ITAR restrictions in the float manufacturing. There are no concerns. So we are aggregating this data in a government-controlled, for official use only site. And so as I've been talking about this data releasability, it's so that we can vet that process of giving the data away to the community, which I have to do. But in case I am collecting something that's very sensitive, which we don't imagine in the program, we are making sure that we have the right environment to do that and do that appropriately in the program. So we aren't exporting all of the mission sensor data yet. We're still in the investigation portion of that, but all the environmental data we plan to release here in phase 1, and we're going to look through that data for the mission sensor data for eventual release in the program. So the thesis is that any one float's data, whether it's compromised, picked up, edited, injected into our data network, isn't a concern. The only concern is in the aggregation and the processing that you do over the multi-thousand nodes and reports.
Great. We have some ideas, I'd say, from some of our listeners I want to run by you. So 3, again, I'll dump them now, and then we can answer them as you want. So the first one is, have you thought of using these in freshwater, for instance, down the Mississippi to the Gulf to track conditions and chemistry in Mississippi? Another idea is float-to-float communication instead of going up to the cloud. And one more idea on sampling air-sea interface rather than just oceanographic data.
So it is air-sea interface now. So I'm going to answer these in the reverse order. We've thought about all 3 of these, but air-sea interface is very interesting to me as we move to more coupled meteorological models of the ocean and the atmosphere. Some very simple things like if a float can tell where it's raining on the ocean surface, I think would add a lot of fidelity to future atmospheric and oceanographic models. So changes in salinity in the ocean to changes in the heat flux from rain type of events from clouds, etc. So we are looking at that ocean surface, and then so if you're a user of that data, tell us what you want to know, and we'll work to get you that product. As for the Mississippi River, Sure, these can be used that way. I was focused on the oceans. I mean, I think the River of Things, one of my performers kind of did a toy kit problem by taking an Arduino and putting it on some river near UNC Chapel Hill and collected a rather interesting data set early in this program. If someone's willing to deploy them for me on the Mississippi, we can talk about that. I think I'm worried really about the boundaries of the river and things getting caught up in that. So I'm not that. It's a little different problem than the ocean environment. And what's the middle one? Something I thought about though. I liked it.
Oh, I already dismissed it.
Sorry, I put Megan on the spot here. You're never supposed to put the moderator on the spot.
Float to float communication.
Oh, so as an electrical engineer and a communications electrical engineer, this one comes up a lot and it's kind of near and dear to me. This is not an ad hoc networking program because the ocean, that surface communications layer on the ocean is a very poor channel. These devices don't have a large height of eye, so to get a reliable channel laterally between floats, I think would expend a lot of energy. So the reason to go to the satellite is, even though it is the most expensive, it's a lot less expensive than building routing tables and communicating laterally across these types of scales.
Great. We're running short on time. I want to close with a question that goes back to the innovation ecosystem questions that we started from at the beginning. If you can talk about why DARPA is the right actor to take on the Ocean of Things program and what your sort of final vision is for this.
Sure. I think it can be summarized. In Hawaii this summer, we had ocean observation. It was a conference. I didn't get to attend, but my teammates did on the government team. And people are imagining this world of at-scale ocean sensing, but there's a little bit of a chicken and the egg problem where, like, who's going to build the sensors first to then do the analysis, or I have this analysis and you got to build the sensors. And there's not a company or really government agency right now as a user to build the full-scale business case. So DARPA is kind of just jumping in feet first into this pond and saying, hey, we're going to show a new way of collecting this data and see if there's value in it. And DARPA is one of those great places where we can make a very large bet at very high risk and try to do something in a completely new way. And we're all right if we fail at this, but we want to bring people into this because we want to see if there's value. And the more value is it, the more potential for ongoing investment there can be. So DARPA is just, I think, the place in government where we can do high enough risk research that's far enough out looking that if there's any possibility of this giving value, and we're not concerned with just transitioning to DoD. Yes, I'm a DoD agency, but the DoD depends on the ocean models to do its work really well. The DoD depends on the meteorological models. It depends on a good functioning nation, and we've transitioned many other technologies that have vast value to outside agencies. So I think DARPA is kind of this right place, and maybe it's just crazy enough an idea that it could succeed. So.
That's great. I hope that our listeners who are interested in reaching out can find more information on the Oceans of Things website, which is oceansofthings.darpa.mil. There were a number of listeners that did comment that they are excited to partner and very interested, so hopefully you'll hear from them soon. We're unfortunately out of time. I really want to extend my appreciation to John Waterston for being with us today. Thank you for sharing the Ocean of Things with us. I also want to thank Jason Ray with DARPA, who's been in the background. You might have heard his voice a little bit. He's coordinated the presentation with John, so we're really happy to have him here too. Also, I want to extend my thanks to my webinar producer, Ann Winya, for making all of our webinars run so smoothly. We really appreciate it. As I mentioned at the beginning of the session, GUIRR hosts these webinars monthly, and our next webinar will be on NSF's Navigating the New Arctic Initiative, which is on February 20th at 1 p.m. Eastern. The convergence of natural, economic, and political change in the Arctic inspired one of NSF's 10 big ideas. So during the webinar, we'll talk about how the Navigating the New Arctic Initiative promotes the diversification of the next generation of Arctic researchers and engages partnerships among international stakeholders. If you're interested in that webinar, you can register on our website, and you can also subscribe to our email list to receive information about that webinar and future webinars. Again, our website is nas.edu/GUIRR. While you're on our website, you can also check out the recordings of all of our previous webinars in the archives, which is where I'll be posting the recording from this webinar. And last reminder, after this webinar concludes, you'll receive an email from us with a link to a short survey, which you can use to give us suggestions for future webinars. So take a bit of time to on this, also what to hear more of. Again, for listening, and please feel free to reach out to me with any questions.